The next indirect source of energy we're going to talk about is wind. And again, just some links here to some other resources and explainer videos that you might find useful. Our energy flow diagram here, uh, I think in the previous section we had a separate box for wind over next to hydropower, but it's actually was already included in the main figure from your book. 1% or so of the incident sunlight coming in uh, ends up driving the energy of wind and ocean currents. That's really a fraction of this thermal energy box that you see up here at the top of the chart, because the reason there is wind is because uh, the surface of the Earth warms up. As it warms up through conduction, it heats the air next to it. That air then expands because it's warmer, and that expanded air is less dense than the surrounding air, and so it is buoyant and rises. And that ultimately is what drives all of the wind currents. Different pressures of the air, which are driven by the different temperatures of the air, and the temperature differences are driven by how warm the surface gets due to sunlight hitting the surface, warming up the air over here, which expands. The air over here has an expand, and you get a flow of the high pressure into the low pressure, the less dense air rising, giving circulation and convection and weather. So because the surface of the Earth is complicated and weather, clouds controls how much sunlight is reaching the surface, you get a very complicated time-dependent patchwork of heating of the surface of the Earth, which leads to a complicated heating of the air, which leads to complicated motion of the air driven by that heating. But there are these global patterns. We saw this graph previously looking at global circulation patterns. If we look at the lower right of the figure, you see an arrow pointing up away from the surface. That's because air near the equator is warmed, rises. It's pushed northward by the air rising up beneath it, and it loses some energy and it sinks at around 30 degrees latitude. Uh, it doesn't make it all the way up to the pole. The reason that this is broken up into three cells in each hemisphere just has to do with the rotation of the Earth. And because of that rotation, we'll come back to that later, these rising and sinking cells that you see over the edge of the Earth here get smeared, and within those cells you get prevailing winds that between 30 and 60 degrees latitude are heading to the east. Uh, Between 0 and 30 degrees latitude, they're heading in the opposite direction because the flow of wind near the surface, the flow of air near the surface between 30 and 60 is heading northward, and between 0 and 30 it's heading southward. And that results in a different drift of the air east or west. And so here in Florida, we're used to paying attention to hurricanes. Those form off the coast of Africa at a low latitude, around 2010 degrees latitude, and the prevailing winds drive them to the west over towards the Caribbean and North America. Uh, Gradually, they move northward because they've got more energy. They're trying to take that thermal energy to the pole. When they get across that 30-degree mark, then you see those hurricanes drift back out to the east, where they dissipate over the North Atlantic, sometimes making it to Europe. Anyway, the bottom line is thermal energy from the sun drives air currents. So how much energy is there? You've got moving air, that's kinetic energy, right? The thermal energy of the air is the random motions of the molecules, but wind is a bulk motion, and that bulk motion of that is a high quality kinetic energy of air. If we imagine constructing a imaginary cube around a parcel of air, there's some mass of that air, and it's moving at some speed, whatever the wind speed is, and so that's got kinetic energy given by 1/2 m, which is the mass, which is just based on the density of air, times the speed squared. The power that you get from that air depends on how fast that parcel moves past your windmill, so you get another factor of the speed of the wind. And so the wind power per unit area is given by this equation that's proportional to the speed cubed. So that means if the speed of the wind doubles, its kinetic energy goes up by a factor of 4, 2 squared, but the power of that wind passing by a windmill goes up by a factor of 8, 2 cubed, 2 times 2 times 2. How do the wind resources vary across the world? Um, More in North America and Western Europe and Australia than in sub-Saharan Africa and South America in terms of wind utilization. Sorry, I said resource, but this is wind utilization. So it's China, Western Europe, North America, and Asia. If we look at the actual total resource, though, we can do the same exercise that we did for solar. What's the total amount of energy available in wind power compared to the total amount of energy used by humans? And compare those two. Well, for solar, it's a little bit easier to understand how we came up with the amount of sunlight hitting the Earth. In fact, you can do the experiment by taking a cup of water outside with a thermometer in it and put it in the sun and see how long it takes that to warm up. And you can get to that 1360 watts per square meter just from doing a simple experiment like that. For wind, it's a little bit more complicated because the wind speeds are varying with time and with different positions around the world. But most of the wind energy is driven by these large global scale currents that are fairly predictable. And it turns out that the total global wind power to within 10 or 20% is 2 petawatts. Um, and the total human energy consumption we've already seen is 480 quads. A quad is 10 to the 15 British thermal units. So let's compare those two powers. Wind energy flow is 2 times 10 to the 15 watts. That works out to 2 times 10 to the 16 kilowatt hours. And the total amount of human energy consumption is about 100 times less than that. So the annual human energy consumption divided by the energy in wind flow in a year is about 1%, 0.008, a little bit less than 1%, meaning wind could supply about over 100 times all of human energy needs. And we shouldn't be surprised at all by that because way back here on this slide, we see that the energy of wind and currents has got this little value of 1% next to that on this flow chart. And we remember that solar could potentially supply 10,000 times human energy needs. 1% of 10,000 is 100. So that's kind of a sanity check. Wind by itself, forget about sunlight, forget about hydropower, any of that other stuff. Wind by itself, if we could harness 1% of wind energy, that by itself would be enough to provide all human energy needs. I have to go through transforming it into the right forms. So that's not a practical solution, but it shows that it's an abundant resource. This map just shows how it's distributed across the United States, and I'm going to flip through these, which you can read on your own. Of course, where you've got wind, the greatest wind power depends on topography. As I said, ultimately this is driven by differential heating from the sun. So it depends on where the sun is shining and the geography and the topography that leads you to large wind power. But a huge amount of it is actually offshore, not on land. And so a lot of the developments of wind power have been aimed at building offshore wind power turbines. So as you see here, this is off the shore of Denmark in the North Sea. You can build them if the ocean isn't too shallow, anchored on the ground, but they're now doing facilities where essentially you're putting giant wind turbines on floating platforms. You can think of like oil rigs or giant floating platforms. You could put wind turbines on comparable platforms. This map shows where wind power plants are in the United States as of several years ago. And while we get lots of thunderstorms and some windy weather in Florida, we don't have the strong, steady flow of wind in the state that's steady, predictable, and at a high enough speed to produce, to make it a logical place to put lots of windmills. How has the wind power utilization been growing? Quite dramatically, not quite as fast as solar has in recent years, but still very rapidly. This is the figure from your book, and I looked online and found this to update that figure. I'm going to go back a slide. Here you see in 2015, that number is a little bit less than 450 gigawatts for the world's wind electricity generating capacity. Updated now to 2019 from the website indicated here, and you can go get some additional information if you're interested. Here in 2015, you see that number of a little bit less than 450 gigawatts, and in 2019, it was up to 650 gigawatts. You see that that 2013 number is less than half the 2019 number. That means it's doubling in less than 6 years. So that means it's growing at more than 10% per year. And this is where the countries in the world that are doing the most with wind, China, the most, followed by the United States and Germany. A huge capacity available for the wind resource. This is, you can see sort of from the scale here how large these wind turbines are now. This particular one is 1.65 megawatts is its rating. Remember that kilowatt hour is about 10%, is about 10 cents value of electricity. In 1 hour, this produces 1.6 thousand of those. And so that is about 1,000 times 10 cents is $100. So this is producing a couple $100 of electricity every hour. For your homework, you'll need to understand this curve and the curve on the next slide, which shows the fraction of wind power that can be extracted from the wind by a windmill. We can't take all of the kinetic energy out of the wind, because if we did, that would mean that the windmill stopped the air. And then if we stop that air, it's going to be in the way of the wind that's coming along, right? So we can't actually pull all of the kinetic energy out of the air. It's not physically possible. And it turns out that the peak amount of power that you can get out of the wind is about 59%. And the fraction of the kinetic energy of the wind that you can get out of the wind with a windmill depends on the wind speed and the construction of the windmill and how it is built, rated. It's designed to sort of have a peak power at a particular wind speed that corresponds to what you expect the wind speed to be wherever you're putting that windmill. So this graph, which you'll use in your homework, shows that for this particular windmill, if the wind is blowing at 15 meters per second, it's producing electricity at 1 megawatt. If the wind is only blowing at 10 meters per second, that red curve then is at a power output of only about 0.25 megawatts. From 15 meters per second up to 30 meters per second, the power output is fairly constant between about 0.9 and 1 megawatt. And then over 30 meters per second, the windmill will stop because it's unsafe in those wind conditions for it to keep blowing. So this curve shows you how you can determine the power output from a particular windmill based on what the wind speed is. And just to wrap it up, we just have some images of windmill installations. These are older, smaller windmills. You'll see a lot of these out west. Newer ones are larger. Here in this figure, you can see the person at the base. That gives you a sense of scale, but even this is smaller than the newest large modern windmills. Of course, the wind doesn't blow completely continuously, completely constantly all the time. It has some variability. It's more reliable and constant in offshore wind, but onshore it's a little bit variable. This figure talks about a uh, sort of interesting way to store that energy so that you can even out the dips and valleys in the production of energy, and that stores the energy by compressing air using the energy generated by the wind turbine when it's very windy to compress air and storing it in a tank. The bottom line is that, like the sun, the wind is not a perfectly um, predictable and continuous source of energy, and therefore that means that storage of that energy so that you can draw on the stored energy when the wind isn't blowing or the sun isn't shining is a crucial part of using this particular resource. So the summary here just reiterates that the total amount of energy available in wind is about 100 times the total world energy demand. And I threw this practice problem on there for you to play around with because when I was Googling pictures of wind turbines, this popped up on eBay, free shipping for $189,900, a 50 kilowatt wind generator turbine. Well, if you could buy that, and remember, you don't have to pay for shipping, and install it, and it actually generated 50 kilowatts of power continuously, which it wouldn't, but if it did, uh, and you could sell that electricity at 12 cents a kilowatt hour, how many years would it take for you to earn $200,000 in your electricity sales from this wind turbine? And then you maybe want to compare that to how long you think the turbine will last before it breaks down or needs serious repairs. So fun problem to play around with, and you can post your solutions if you want on Piazza.